Okay, welcome back. There's this packet I passed out called Pretty Pleasing Pigeonhole Principle Problems. And on page 4 of this packet is a whole bunch of problems, all of which are just so hard. So this is problem number 1 on page 4. And here's what it says. Take an arbitrary sequence of integers. They could be positive, negative, 0, there could be repeats, whatever. So pretty general. You have m integers in some kind of a sequence. The claim is, sort of shockingly, that there is some partial sum or some consecutive sum of members of this sequence which is divisible by m, the length of the sequence. Alright, I don't think I had any, I was told immediately how to do this problem, not really being given the opportunity to think about it. Let's just maybe do a little example really quick just to see what's going on. So here we go. Here's an example. Take the following sequence of 5 integers. 4, 7, 8, 23, 27. Okay. And what this theorem is saying is somehow I can take consecutive sums of consecutive members of this sequence, and there must be some sum of consecutive members of the sequence, which is a multiple of 5. Well, you can just start trying to do some crap, man. Like, I don't know, what's 4 plus 7? That's 11. Is that a multiple of 5? No. How about 4 plus 7 plus 8? Well, that's 19. That's not a multiple of 5 either. 4 plus 7 plus 8 plus 23. That's also not a multiple of 5. 19 and 23 is 42. And 4 plus 7 plus 8 plus 23 plus 27 is also not a multiple of 5. That's 69. Alright, and by the way, maybe just we mentioned that, 4 itself is not, because you could have a sequence of length 1? No, you can't, sorry. K now have to be different. So that's actually like irrelevant. Alright, anyway, point is, if I am doing this right, suddenly I am doubting myself. Yeah. In terms of, oh, I see. Okay, so no, I actually do want to talk about 4 as well, even though, well, you'll see. Okay, so notice that it didn't work, right? None of the partial sums, where we think of partial sums in the traditional way, sum from the beginning to that point in the sequence, none of those satisfy. But notice that we don't need to start at the beginning, a sub 1, we can start sort of just anywhere. Hold on, I'm just confusing myself for a second here. I guess you can have a sequence of just length 1. Because even though K and L are different, I start counting here. So if L is K plus 1, then that's just a sequence of length 1. Okay, so you can have a sequence of length 1. So for a different example, suppose I had just maybe like 4, 7, 15, 16, 17, for example. Well, here you could just take 15, and that sequence of length 1 would satisfy the theorem because it's a multiple of 5. In this case, K would be 2, and L would be 3, and you would just take the third term, which is 15. Okay, anyway, that was a little technical. Point is that this didn't seem to work, but we have access to more sequences than just this. We have access to, I could do, well, just 7 and 8, for example. And that already is 15, and so we win. So what's the sort of points behind this, or how should we be thinking about this? Well, what I now want you to do is to consider these partial sums and to notice that, well, the thing I already said is that if any of these partial sums, partial sums, you know, in the traditional sense, starting from the beginning, is a multiple of 5, then the theorem is done. But if none of them is a multiple of 5, well, then each of them must have some non-zero remainder when divided by 5. But, for example, 4 is just equivalent to 4 mod 5. And 11 is equivalent to 1 mod 5. But now, suddenly, here we see that 19 is equivalent to 4 mod 5. And in fact, that just always happens that the remainders, after being divided by, I guess there's one way of putting it is, if you have 5 partial sums for the 5 terms of your sequence, then if any of them is a multiple of 5, we're done. But if none of them is a multiple of 5, then 2 of them must be equivalent mod 5. Because by the Pigeonhole Principle, there are only 4 possible non-zero remainders, but we have 5 partial sums. And so, what is the significance of these both having the same remainder mod 5? Well, then you just take this sequence out of this one. And in fact, that gives us that gives us the final answer to this problem, which is that you want 7 plus 8. So that's just what happens when you subtract the 4 out of that one. Okay, maybe this will make more sense, phrased in the abstract method of proof. So here we go. What I now encourage you to do to do this problem is to consider the following sequence. This is the sequence of partial sums. The first member of the sequence is A1. The second member of the sequence is A1 plus A2. Then A1 plus A2 plus A3. And we go all the way out to the final member of the sequence, A1 plus A2 plus all the way up to AM. Okay, so we have here now M partial sums. So observation number 1, if any of these M partial sums is a multiple of 5, is a multiple of M, we're done. Because that's all the theorem claims, that there's some consecutive sum of the elements of the sequence which is a multiple of 5. Okay, good. And yeah, just to clarify, that would be in the theorem, that would be equivalent to setting k equal to 0. So you'd start with the first term, you'd go all the way to the whichever one it is. Okay. But then else, if none, on the other hand, so this is a proof by cases, I guess, if none of the partial sums, is a multiple of 5, then multiple of M, then kind of as we just said, okay, I don't think I need to write this all out because we sort of did it over there in the example. If none of the partial sums is a multiple of M, then it means they all have non-zero, then each has non-zero remainder, then each has non-zero remainder when you divide by M. But then there are, in fact, M partial sums and only M minus 1 possible non-zero remainders. So that's exactly what we said over there, right? We have M partial sums, M partial sums, and M minus 1 possible non-zero remainders. So, by the Pigeonhole Principle, there must be two partial sums with the same remainder after dividing by m. And so, I'll just cut right to the math. What we must have some a1 plus a2 plus partial sum going up to, say, al. Let L be, well, we must have two partial sums. I'll just do it like this. Let L and K be the two different, the indices of the two separate partial sums which have the same remainder upon dividing by m. So we have some non-zero remainder, and now, just as before, you just subtract these two equations. Let L be bigger than K, I guess. So let L be bigger than K. So without loss of generality. Then when we subtract, what we get is a sub k plus 1 plus a sub k plus 2 plus all the way up to a sub L, and it is in fact just b minus c m. And so we win. We've shown that m divides the sum of the numbers from that point. Okay, good. This second problem now is about a chess master. This is a follow-up to the previous problem. I think I'll just erase all of this. And here we have a situation in which there is a chess master. He is training for a chess tournament, and man, this board is just trashed somehow. I don't know what happened. It's getting worse and worse. Okay, here we go. The chess master, he has 11 weeks to prepare for a tournament. And he decides to play at least one game every day. So every day at least one game, possibly 2, 3, etc. But in any given calendar week, he is not going to play more than 12 games. Show that there must exist some succession of consecutive days during which the chess master will have played exactly 21 games. Okay, and my class several years ago figured out that in fact I don't need 11 weeks for this. This is going to happen by the end of week 3. So claim the chess master will have played exactly 21 games. 21 games in consecutive days by the end of week 3. Okay. How? Well, let's introduce a notation in which he plays. Let's just say that he plays A1 games on day 1, A2 games on day 2, etc. Okay, note that he plays at least one game every day. So all of these numbers, A1, A2, etc., they're all integers, positive integers, and they're all at least 1. Now he also doesn't play more than 12 games in a given week. So what can I say about A1 plus A2 plus A3 all the way up to A7? This is the sum of the games that he's played during the first 7 days. Well, it's got to be at least 7 because he plays at least one game a day. But now, well, this is exactly the statement in the problem. He does not play more than 12 games during any calendar week. So this is 12. Similarly, if I think of how many games he plays from the beginning all the way up to the end of the second week, then as he, I think all of this is actually necessary, right? Since once again this is at least 14, but since he didn't, whew. Whoa, my children are screaming downstairs. I'm ignoring them. This has to be less than or equal to 24 because why is this true? I mean, it's sort of obvious, but let me try to articulate it anyway. Oh my god. Because oh boy. Yeah, he doesn't play more than 12 games in a given week, so he plays max 12 games in week 1 and max 12 games in week 2. So the first 2 weeks together, of course, he plays less than 24 games. And then the last one is if we just consider, oh man, my family is going to be so mad at me. If we consider all the games up until a sub 21, oh man. Jesus. Ada, stop crying. Alright. I don't think I can do this. I'm gonna stop this video. Okay, we're back. Anyway, here we go. By the end of the third week, since you can't play more than 12 games in week 1, you can't play more than 12 games in week 2, you can't play more than 12 games in week 3, then we've played a total of 36 games. Okay, and at least 21 games through those 3 weeks. Well, now we're going to do almost the exact same thing as in the previous problem. We'll now consider the following sequence. And the sequence that we're going to consider is the sequence of partial sums. So A1, A1 plus A2, A1 plus A2 plus A3, all the way up to A1 plus A2 plus A3 plus, ending with A21. Okay, so this is just what you think. Number of games played by the end of day 1, number of games by the end of day 2, all the way up to number of games played by the end of week 21. Now, as before, oh, and note that since each a sub I is greater than or equal to 1, this will become crucial later, he plays at least one game every day. That means the terms of this sequence are all distinct. The terms of this sequence are all distinct. In fact, this is an increasing sequence of distinct positive integers. Okay, well, just like before, if any of these, just pausing for, oh yeah, if for any n, if for any n, the sum from A1 to AN is 21, then we're done, because that's exactly what we want to show, that there exists some sequence of consecutive days in which the total number of games played is exactly 21. So if the cumulative sum starting from the beginning ever hits 21 exactly, then we're done. But if not, then now we just consider remainders, after dividing by 21. If not, then each of the cumulative sums, A1 to AN, has non-zero remainder when dividing by 21. Wait, hold on. Yeah, yep. Okay. Because this, just to be clear, this sequence here in purple, there are 21 terms in this sequence, of course, because there are 21 partial sums, the partial sums for the first 21 days. And if there are 21 terms in the sequence, but none of them, this is the moment at which we note that since the sum from, I knew something was missing, since the cumulative sum all the way to 21 has to be less than or equal to 36, then I don't need to worry about other multiples of 21. In other words, 42 or any other higher multiple of 21 is irrelevant in this case, because the chess master simply just can't have played 42 games can't have played 42 games in the first 21 days, because that would violate the don't play 12 games in a day in a calendar week thing, and therefore it must be that if the cumulative sum is not 21, then it is in fact not a multiple of 21 either, and so it is a number which has non-zero remainder when dividing by 21. And then we just do it again, right? By the Pigeonhole Principle, since we have 21 partial sums, but only 20 possible non-zero remainders, then it means that two partial sums have the same remainder. Okay. Well, following the notation of the previous, not following the notation of the previous problem, it must be the case that, for example, so say for m and n, let it be that a1 plus a2 plus all the way up to an is 21 q1 plus r, and a1 plus a2 plus all the way to am is 21 q2 plus r. In other words, where r is in this case, we're assuming that these cumulative sums are not multiples of 21. So in other words, the remainder is non-zero, but of course the remainder has to be less than 21. In other words, we just applied the Euclidean division algorithm to these two partial sums, the sum up to day n and the sum up to day m, where without loss of generality n is less than m. Okay, and now just as with the previous problem, we subtract. And if we subtract, hold on a second. Maybe I don't even want to subtract per se. Maybe I just want to say that, hold on, I lost my train of thought for a second there. What am I trying to show? I'm trying to show, okay. So notice that, okay, I see. So now here's what we know. We know, unlike in the previous problem, when it was an arbitrary sequence of integers, possibly including some repeats and positives and negatives and stuff like that, since this sequence, the sequence in purple, is increasing by at least one each time, that all these things are distinct. So since all these are distinct, it is impossible for two of these to be exactly the same. It's impossible for two partial sums to be the same. And so once I've expressed these two partial sums in these two different ways, then I can say for sure that Q1 is not Q2. And also, if Q1 is not Q2, what are the possible values for Q1 and Q2? Well, could Q2 be 2? No. Because if Q2 is 2, then by day M we must have played like 43 games or something like that. But we know from this line here that in fact the partial sums have to be less than or equal to 36 for all of the numbers under consideration. And so since 21 Q2 plus R has to be less than or equal to 36, we can say that Q2 has to be less than 2. It can't be 2 or higher. And all right, well there we go. Right? If Q1 and Q2 are integers and positive integers, and Q2 has to be less than 2, and Q1 is less than Q2 because n is less than m, and they also have to be different, then the only way to satisfy that is if in fact Q1 is 0 and Q2 is 1. Why is that important? Well, that means that in fact on day 1 to up until n, we played exactly 21 plus r games, and on day 1 up to day m, we played r games, because Q1 is 0, and on days 1 up to m, we played 21 plus r games. And now we subtract. And if we subtract, we see that on days an plus 1, on day n plus 1 and day n plus 2, all the way up to day m, we played precisely 21 games. Okay, so that was an extremely careful explanation, but hopefully that was clear. Okay, let's just keep on going now and do another problem. This is a problem on page 5. Okay. Okay. So, here we go. Here is a problem on page 5. Here's what it says. Show that for given any 52 integers, there exist 2 of them whose sum or else whose difference is divisible by 100. There exists a pair for which either the sum or difference is divisible by 100. Okay. Divisible by 100. Alright. I got this problem just barely. It's not super hard, but starting to get pretty hard. Alright. Given any 52 integers, there exist 2 of them whose sum or whose difference is divisible by 100. Alright. So, this is going to be sort of a proof by, it's gotta be. You can think about what it would take to sort of break this theorem or something like that. So, how could you avoid it? Or maybe what kinds of things suffice for there to be a sum or difference divisible by 100? So, the problem is that we have 52 integers, so they could be anything, right? You could just have, a lot of really, really big numbers. 4, 7,000, 6, 51, whatever. A lot of integers. There are 52 of them. Why must there be a pair for which the sum or difference is divisible by 100? Well, first of all, if there are any 2 of them, which add to 100, then that would be done. If there are any two of them which add to a multiple of 100, that would also be, we would also be done. And then the differences, right? If there are any two of them for which their difference is divisible by 100, then that also, so okay, so here, for example, here there's a pair for either sum or 100. So now what I kind of want to do is say, lost my train of thought here for a second. So okay, so if you had 4 and like 96, if 4 and 96 were on the list, well then just grab them, because those two together, when you add them, have a sum of 100. Okay, but also if you had like 103 and 97, then you would want to sort of grab them too, because they would not add to 100, but they would add to a multiple of 100. So anytime this sort of remainder after dividing by 100 is, well, I just won't say anything yet. Now let's consider the fact that if their difference is divisible by 100, then that also suffices. So, okay, so what does that mean? That means if you had like, 114 and, well, 14, then you could subtract them and you could get something which was a multiple of 100. But then also we should consider, and so, okay, so maybe this is already kind of enough. What we want to now do is we want to sort of split them up in this kind of a way such that numbers which are going to add to 100 are in the same sort of box. So think about the boxes like this. Take like 1 and 99. Put those together in a box. If your two numbers, you have these 52 integers, right? If your two numbers are 1 and 99, or any number which has remainder 1 after dividing by 100, or remainder 99 after dividing by 100, then put those together in a box. And if your two numbers land in that box, well then clearly their sum is going to be a multiple of 100. And then just keep doing that. Take a box with 2 and 98. Take a box with 3 and 97. And just keep on going all the way up to, I guess, like 49 and 51. Okay, so if I did this correctly, there are going to be 50 boxes there. No, 49 boxes, of course. There are 49 of these boxes, and what are these boxes? They're basically just remainders after dividing by 100. And now, of course, what's the other possibility is that you could have remainder 0 after dividing by 100. And another possibility is that you could have 50 after dividing by 100. And I want to treat these separately because if you have two numbers which both have remainder 0, so maybe I should just start writing. This is a terrible explanation, but basically now take for each of the 52 integers, take their positive remainders mod 50, mod 100. which is just to say for each of these numbers, for any number n, just express it as q q100 plus r, where we've seen r is positive and less than 100. Okay, so the remainder is always positive. And now, considering the remainders, because anything over 100 is just stupid. So of course we want to focus on the remainders mod 100. Now we see that there are these 52 sort of different boxes. 49, 50, no, 51. So we have 51 boxes and 52 numbers. So by the Pigeonhole Principle, there are two numbers in the same box. Better to say, there is at least one box. There is at least one box with at least two numbers in it. And now we go by cases. If the 0 box is the box with two numbers in it, then what that means is that there are two numbers out of my 52 which in fact have, are divisible by 100. Well, then just either add or subtract them. It doesn't matter. If you give me, right? Yeah. Yep. Just let's say, yeah. If you add, yes, right? Yeah. If you add two numbers, which are divisible by 100, of course, you'll get a sum which is divisible by 100. And if you subtract two numbers which are divisible by 100, you'll get a number which is divisible by 100. So if the two numbers fall into the 0 box, great. If the two numbers fall into the 50 box, this is the part I thought was a little bit subtle, then what that means is that, well, you have these two numbers which have remainder mod, which have remainder 50 mod 100. Well, then you just add them. If you have two numbers with remainder 50 after dividing by 100, then when you add them together, their sum will be a multiple of 100. I guess their difference will also be a multiple of 100. So there you go. All right. So the more interesting case is what happens if the two numbers, and remember the Pigeonhole Principle guarantees us that there's at least one of these 51 boxes with two numbers in it. So take the 397 box. What does this mean? It means that we must have some number, say, call it A, which is of the form 100q plus 3, and there's some number B out of our 52 original numbers, which is the form 100q plus. Oh, actually no, it's more complicated than that. All it says is that within this box there are two numbers. So I guess there are three possibilities, right? Either A and B both have remainder, so I should use a different Q here. So Q1, Q2. Either A and B both have remainder 3 after dividing by 100, or A has remainder 3 when dividing by 100, and B has remainder 97, or vice versa, or they both have remainder 97 when dividing by 100. The Pigeonhole Principle guarantees that since there are 52 integers and they may have 51 boxes, then there must be one box with at least two numbers in it. And taking sort of arbitrarily the 397 box, then that box must have at least two numbers in it. So take two of the numbers in that box, again arbitrarily. Either they have the same remainder after dividing by 100, being 3, in which case, of course, if you subtract them, now you'll get a number which is a multiple of 100. And if they both have remainder 97, then again, if you subtract them, you'll get a number which has remainder which is divisible by 100. And here, if they have sort of opposite remainders, so to speak, then they're perfectly matched up, so that when you add them together, you'll get their sum is a multiple of 100. Okay, good. That was terrible. Okay. Let's go. We got 10 minutes to do this. This is this packet, a pretty pleasing Pigeonhole Principle problems packet. This is number 4 on page 6. This problem is just ridiculously hard. I got this problem out of a book. I had no idea how to do it. I just put it on a packet. I passed it out the first year. I never talked about it, never looked at it, never tried to do it, never told anyone how to do it. And I think that probably happened for several more years in a row, until finally one year, I think 2 years ago, this kid, Alex Wong, tried really hard to do this problem. And he was just getting desperate. He was just like, Mr. Rose, I can't do any of the problems in this freaking class. This class is too hard. He said he tried for like an hour. He's a pretty smart guy to do this problem. He got nowhere. And he just asked me in class one day, he's like, Mr. Rose, these problems are impossible. Can you even do this problem? Do you know how to do this problem? And I had to admit to him that I hadn't even really looked at this problem yet or tried. And he said, all right, you go. He said, you go, Mr. Rose. You go try to do this problem. Because he figured that he was about as smart as I am. That's probably about right. And it took me 90 minutes. And 90 minutes of intense, solid concentration. I solved this problem, kind of just barely. Here we go. This is the problem. 100 integers are chosen from the set 1, 2, 3, all the way up to 200. And one of the integers chosen is less than 16. If you guarantee to pick one of the numbers which is less than 16, then there must be 2 of the numbers such that one of them is divisible by the other. Okay, and the idea here with this whole, like, one of them has to be less than 16 is that small numbers are particularly problematic. If you choose, say, the number 1, well, then 1 divides everything. And so you'll definitely be able to find 2 numbers such that 1 divides the other, because 1 and anything have that property. And if you pick 2, then also, since 2 divides all the even numbers, then it should be pretty easy to find 2 and any of the even numbers in this set, such that 1 divides the other. And so small numbers are particularly disastrous if you are trying to avoid having the property that there are 2 numbers such that 1 divides the other. And so what this theorem says is, if you pick at least one small number, where in this case small means less than 16, then you're guaranteed to have this property. Okay. Well, here we go. How are we going to do this? What we're going to do is similar to a problem we've done already. We're going to factor out powers of 2. And what we're going to do is we're going to construct these by factoring out powers of 2. Then we take, for every number, we apply the fundamental theorem of arithmetic, and we express that number as powers of 2 times the product of all the other odd primes, which is in fact odd. So what we have are these kind of columns. This is how I initially thought about it, or sets. You have sort of this set 1, and what is this set 1? It's 1, 2, 4, 8, 16, 32, etc. In other words, it's all the powers of 2. And then you have set S3. What is S3? It's 3, 6, 12, 24, etc. And here we go, we're just going to keep on doing this. Then you have set S4, which is 5, 10, 20, 40, I might need to go higher here, 48, 64, okay, and I see already that I'm not going to finish this in time, because I have to go in a second, but, so here's S5, this is, sorry, this is not S4, this is S5, and this would be S7. In other words, for every single so factor out all the powers of 2, and then consider the numbers in these kind of columns like this, 28, etc. Okay, how far out do we go? Pretty far out. Well, I'll just go a couple more steps. S9, 9, 18, 36, S11, 11, 22, 44, etc. Okay, and here is the key insight. The key insight, I guess, or an initial insight, is that you can't ever pick two numbers from the same column. Because what are these columns? These columns are just, it's every odd number, basically, and all of its, it's, how do we say this? It's every odd number, and it's multiplied by various powers of 2. And so if you take any two numbers from one of these columns, then they are going to be I guess the smaller number automatically divides every higher number up in this column. And so if we have, I should mention I'm going to be proving the contrapositive. And the contrapositive, to show that having chosen 100 numbers and one of them is less than 16, that there are two such that one is divisible by the other, what I'm now going to do instead is, I guess it's sort of a proof by contradiction, I'm going to suppose that no two of the integers has the property that one divides the other, and I will prove that then we must not have taken any of the numbers 1 through 15. And so factor every one of the 100 numbers into this form, where it's like leading powers of 2. So for every single number n, express it as some power of 2 times the product of all of the odd prime factors. And we see that that partitions every single number. Now we're listing the numbers essentially by their value of q, if I've done this right. Yeah, these indices here are the q's, which are always necessarily odd. And the last one would be S199, which has only one number in it, which is 199. And so the intermediate conclusion is that if no two of the numbers has the property that one divides the other, then we can't ever choose two numbers from the same column. And since there are precisely 100 of these columns, because there are 100 odd numbers between 1 and 200, and we have chosen exactly 100 numbers, then in fact we must have chosen, by a sort of variant of the Pigeonhole Principle, we must have chosen precisely one number from each column. Okay, if we've chosen precisely one number from each column, I will now show that we can't possibly have any of the numbers 1 through 15. I will do this in a minute. Okay, we are back. Sorry, there were some distractions, so this is now several hours later, but let me just explain what's going on again. Same problem, of course. We have a set of 200 integers, 1, 2, 3, all the way up to 200, and we are going to choose 100 of them. And the claim is, if there are no, if one of the numbers that we choose is small, and here by small we mean less than 16, then two of the 100 numbers that we have chosen must have the property that one of them divides the other. Okay, and we are going to prove the contrapositive. And so what we're going to prove is that if we have chosen 100 numbers from the set 1, 2, 3, all up to 200, and none of them no two of them have the property that one divides the other, then we must not have taken a small number after all. We must have taken only large numbers. Of course it's quite easy to choose 100 numbers it's quite easy to choose 100 numbers from the set 1, 2, 3, all the way up to 200, such that no two of them divide each other. For example, as we mentioned in the other video for the other theorem that was in Gossett, we can take 101, 102, 103, 104, all the way up to 200. That is a set of 100 numbers. It's the 100 largest numbers of this set is a set of 100 numbers such that no two of them divide each other. So in general, it's not hard to choose 100 numbers out of this set such that no two of them divide each other. What we showed in the other video, the other theorem that was earlier in this packet, is that if you take 101 numbers, then two of them must divide each other. Here we're looking at it from a different perspective. We're saying, well, we're still only taking 100 numbers, and though it might be easy in general to take 100 such that no two of them divide each other, if one of those numbers is small, then one divides the other. And here small means under 16. Okay, so back to the proof itself. What have we really done? We have observed, so now we're in the following world. We have taken 100 numbers, no two of them divide each other, there are no two of them such that one divides each other, and we're going to show that 1, 2, 3, 4, 5, 6, all the way up to 15 simply can't be among the numbers that we've chosen. And if we can show that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15 have not been chosen, then we're done. Okay, well why can't any of those small numbers have been among our choices? So now what we're going to do is, and we've done this before already, so I won't make that big of a deal about it, is for every single one of my 100 numbers, I am going to, or in fact actually for every single number in the set from 1 to 200, I am going to factor it. According to the fundamental theorem of arithmetic, there's a unique way to factor a number as a product of primes. And it's going to have some numbers of 2's in it, where this number k is greater than or equal to 0, so if k is 0, then the number n was odd. Since 2 is the only even prime, all the rest of the primes factors of n will be odd. The product of a bunch of odd numbers is odd, so q is an odd number, which is the product of all of the odd primes in the prime factorization of any one of the numbers. And we're going to do it for every single one of these. And we see that, and now what I've done is I've sort of organized in a kind of a chart. I should probably use colors here or something. I have partitioned every single number, 1 to 200, into a bunch of distinct subsets, that's just what a partition is, based on this value of q. For any number whatsoever, there is a unique value q, which is simply the product of all the odd primes in the prime factorization of that number. And so let's categorize all the numbers in the set, 1, 2, 3, 4, all the way up to 200, by that q value. And so what is S1? S1 are all the numbers whose q value is 1, and that is simply the powers of 2. What's S3? S3 are all the numbers in the set 1 to 200 whose q value is 3. So just 3 itself, and then 3 times 2, 3 times 4, 3 times 8, 3 times 16, etc. And of course this stops eventually. These lists are not infinite. The largest power of 2, which is an element of the set 200, is, I guess, 128. So in fact, these lists are not that long at all. Maybe it's even worth it to just do them all. I don't think I want to do that. But here we get 96. And then this 192, and then it just stops there. And the rest of them will be even shorter. Here we get 80, 160, and then we stop, etc. Okay, so having done that, having organized the numbers into these columns, this is all a repeat from the first video, but maybe this is better now. What's the claim? So every single one of the numbers 1 through 200 appears somewhere in one of these columns. I've left some blank space over here because I'm not going to write out every single one of them. Now we make the observation that since on the assumption no two of the numbers in our subset, we've chosen 100 numbers, no two of them divide each other, then we see sort of immediately that you can't have two numbers, we can't have chosen two numbers from the same column. Because for any two numbers in this column, they differ by a power of 2, and so the smaller one will divide the larger one. In fact, that's a property of all of these, all of the subsets of this partition, that for any number in any one of these subsets, it divides any larger number in that same subset. Okay, these go all the way up to 199, and so now we see that there are in fact 100 exactly of these subsets. There are 100 odd numbers between 1 and 200, 1, 3, 5, 7, etc., all the way up to 199. And since we have chosen 100 numbers, and there are 100 odd numbers, and we can't choose two numbers from the same column, then we must have chosen exactly one number from each column. Okay, now that we know that we've chosen exactly one number from each column, we can start to kill some numbers and to realize that they can't possibly have been chosen. So, for example, we cannot possibly, and I will now kill it with red, choose the number 1. And okay, that's because no two numbers that we have chosen in our set of size 100 have the property that one divides the other, and one divides everything, so we can't have one. But we also can't have 3. Why is 3 impossible? Well, 3 is impossible because we must choose one number from every single one of these columns, but that means we have to choose a number from column S9. So one of these numbers must be represented, 9, 18, 36, etc. These are the numbers whose odd residue is a real word, that means a real thing. So I don't know what the word here is, but we must choose one number from the column of all representing all the numbers such the product of the odd primes is 9. And yet 3 divides every number in this column. So since 3 divides every number in S9, then and we have to choose a number from S9, then we can't choose 3, because it would divide every number in this column. And now we start to see what is going on here, right? I'm going to throw in some dots. 5. This is what we want to do. Yeah. Actually, for 5, we see that, okay, there's a lot of different ways to do this, but there's one way which is sort of more clear. So what about 5? Is it possible that we choose 5 among our 100 numbers? Well, I say no, because there are other columns coming, such as 15. What is the 15 column? It's going to contain numbers like 15, 30, 60, 120, etc. And yet every number in this column is a multiple of 5. And so if I must choose a number from this column, then I can't have 5 among my final subset, because it would divide every number in this column. And then we'd have 2 numbers, one of which divides the other. It's also true that you could maybe just go straight to 25 as well to make that observation, but here I think it's more clear. Okay, and we just keep on going, man. We can't have 7 because the number 7 cannot be among the ones chosen, because when we get to column 21, we must choose a number from column 21. What is column 21? It's 21, 42, and 84, etc. And so every number in that column is a multiple of 7. And what we're really doing here is we're just multiplying by 3, like the next biggest prime is really what's going on. It's like we factor all the leading 2's out, and now we're considering 3. Can I have 9? No, I can't have 9, because 9 divides 9 divides every number in column 27. I can't have 11 because 11 divides every number in column 33. I can't have 13. I guess I should include 13 here because it's one of the numbers I care about. So here's squeezing it in a little bit. Here's S13. What's 13? It's 13, 26, 52, etc. Can I have 13? No, I cannot, because 13, the number 13 itself, divides every number in column 39. And where does this end? Where does this conversation end? It ends when we finally get to 65, believe it or not. When I get to S65, finally, I realize that this is the first column, this is step 1, in which, what are these numbers? That's 65, and then this is like 130, and that's it. What is the significance of 65? 65 is the last number, which I can say for sure is not one of the numbers 1 through 100 that I have chosen. What makes 65 impossible? 65 is impossible because 3 times 65 is 195, and 195 is one of my columns. And I have to choose a number from column 195. There's only one number in column 195. It's 195. And 65 divides 195. So since I need to choose one number from every column, and therefore I need to pick 195, so then I can't pick 65. So what's happened is the first row, so to speak, in every one of these sets has been excluded by virtue of the fact that if you multiply that odd number by 3, then it's still less than 200. It's still an odd number less than 200, and it represents a column which we must take one number out of. And so I can't have 21, for example, because 21 times 3 is 63, and I need to choose a number from column 63. And 21 divides every number in column 63. Okay, I think you get it. Okay, having done all of those, we now exhale and start looking at column 2. What's column 2? Well, column 2 is a bunch of other things. And now we see, okay, can 2 be one of the numbers 1 through 200 that I have chosen? And the answer is no. Because having already excluded 3 from column from set S3, every other number in S3 is a multiple of 2. It's even. And so is that what I want to do? Yeah. And so I can't choose 2 because 2 divides all of the other numbers that I haven't yet excluded in column 3, and I need to choose exactly one number from each column. Okay, can I choose 6? Well, also no, because 6 divides every number left in S9, 18 and 36, and I must choose a number from column S9. Can I choose 10? Well, also no, because 10 is going to divide every number left in S15. 30, 60, 120, etc. So 10 is out. Can I choose 14? Also not, because 14 divides 42 and 84, etc. 14 divides every number left in column S21. So 14 is gone. Alright, and we keep on doing that. Where does that stop? It actually stops later. Who cares? I think we've done what we need to do. Now we go back and we do it again. Third row. Can 4 be one of the numbers chosen? No, because 4 divides every number left in S3. And can 12 be chosen answer? No, because 12 divides every number left in column 15. Hold on. 12 because S9? S9. Yep. Oh boy. Sorry, I did need to be a little bit more careful here. The logic depends on me also excluding. So this means that I should draw. Oh man, I thought I got lucky and almost had it perfect. But I should keep going all the way up to S27. This is a little bit subtle. What's in column S27? 27. Of course, 54, 108, and that's it. Is 27 possible? No. 27 is not possible because if I choose 27, then column 81, which is a column, and it is, and actually this is deep, this is important, I'm glad this happened. Well, it was bound to happen, but if you take column 81, what does it look like? It looks like 81, 162, and then that's it. So I have to choose a number from column, I have to choose a number from column 81, and when I get to column 27, I realize that I can't choose the number 27 itself because column 27, because 27 divides every number in S81, and I have to pick a number from column 81. So since 27 was already excluded in the first line, then when I got to this 18, I realized that 18 in round 2 was also excluded. Why? Because 18 divides every number left in column 27. 18 is a factor of 54, 108, etc. And so that's out. And in fact, the round 2, the green ones, they end with somewhere around column 42 is where that finally, no, column 63 is where that, never mind. I think this is good enough, hopefully. So it is now that I realize, and I think this is almost the last one. Oh boy, I might have to do more backtracking. I'm getting sad. 12, is 12 possible? No, 12 is not possible because 12 divides everything in 12 divides everything left in column S9. So maybe just let's flesh out S9 a little bit. It was 9, 18, 36, 72, 144, and then it stops. And 9 was eliminated because 9 divides everything in column 27. 18 was eliminated because 18 divides everything left in column 27 after 27 itself was eliminated, since it divides everything in column 81. And now everything remaining in column 9, and I have to choose one from every column, is now a multiple of 12, and so 12 is impossible. Okay, 20 is also impossible because 20 divides everything in column 21. What? No, that can't be right. In column 20, in column 15. Is 15 here? Yeah. 20 divides, okay. Because once again I failed to bother taking my green X's out far enough. Oh boy. But 22, it can't be there because it divides everything. Yeah, just trust me. This process keeps on going. 30 is impossible because 30 divides everything in column. 30 divides everything in column. Oh my god. Why is 30 impossible? Because 15 times. Let me just backtrack a minute. 17 because it kills everything 27. 30 because it kills everything in divide by 6, 9 times 3. In column 45, yeah. So 30 divides everything, 30, not going to draw this, but 30 divides everything left in S45, and starting with 90, and 45 itself was eliminated because it divides everything in column 135. Okay, so since 30 is not allowed, then 20 is not allowed either, because 20 divides everything left in column 15. So we'll kill this. Okay, let's just go through our numbers. What do you got? 1, 2, 3, 4 is gone. 5, 6, 7, 8 is still, we need to talk about. 9, 10, 11, 12, 13, 14, 15, and here we go. The final step. Why is 8 not allowed? Well, the answer is that 8 is not allowed because 8 divides everything in column S3. I have to choose a number left in column S3, and everything in S3 is a multiple of 8. And so we stop. That's it. We have now, by sort of casework, excluded every number 1 through 15. And thus I've backed up my claim that we have not chosen any number from 1 through 15. Okay, this feels extremely kind of convoluted and weird. If I had a little bit more board space, I maybe would actually write all 100 numbers from odd numbers and list all 200 numbers out, and it makes it actually feel a little bit more real to really take the process out to the bitter end. There's this sort of strange exclusion that's happening, and I'll tell you that that it does stop. 28 gets excluded, but that's the end. And the last one in row 2, I did this out, is 42 gets excluded in round 2, and the exclusions in round 1 stop at 63. So I don't have any space to include that. But so I'll just do something like this. Cha cha. There's this like weird sort of triangle shape of numbers which can't possibly be there. And what is the rhyme and reason to this? It sort of has to do with powers of 3. If you look at 81, 81 is 3 to the 4th. And the sort of point that the sort of, this is going to be a bad explanation, but the moment at which this process got some kind of logic to it, actually, was right here. The fact is that the highest power of 2, the highest power of 3, oh my god, I'm not going to be able to say this properly. No, it's not really 162, it's 81. It's the fact is that 81 is 3 to the 4th. And so, okay, so you're probably saying, okay, sure it is. That is just a true fact. 3 to the 5th is already 243, which is outside my set. And so if I'm only considering the numbers 1 to 200, then this process kind of terminates here at column 81. 81 is the largest power of 3, which is less than 200. And since I must choose a number from this column, that is what is sort of forcing 27 to therefore not be a member, to not be one of my numbers chosen, because 27 divides every number in this column. And the fact that I can't choose 27 means I must choose 54, which is what told me that I can't choose 18, because 18 divides 54 and 108. And the fact that I can't choose 18 means that I have to choose 36, 72, 144. And the fact that I have to choose 36 is why I couldn't choose 12, which was the sort of the last number to get excluded, or the hardest number to exclude, so to speak. Or really, and then finally, because I couldn't choose 12, I couldn't choose 8, because 8 had to divide some number left in column S3. So if you, the answer to making this seem not just like a crazy, stupid exercise in casework is to conclude that there was actually nothing special about 15 per se. The numbers 1 through 15. 15 just happened to be 1 less than 16. And 16 is a number that, this is the sort of the interesting number. What this says is that this sort of theorem extended out in a more general case says that given some bunch of numbers, a lot of them, starting from 1 all the way up to some point, who knows, very big number. So 1 to, man, I hope I'm doing this right now. 1, 2, 3, all the way out to n. No, let it be 2n. Then, here's what this theorem says in its fully generalized form. I hope this is right. That you can, if you pick n of them, I think I'm not going to quite be able to pull this off. If you pick n of them, and I'll just do it in the contrapositive form, and no 2 of them, divide each other, then you didn't pick, in our example, it was you didn't pick any numbers from 1 through 15. But more generally, you didn't pick any number up to 1 less than some power of 2, where that power, the power indicating how far to go, in this case was 16, whoa, where m is in fact, is such that, oh my god, this sucks, is such that 3 to the m is less than 2n. So it's the size of the appropriate power of 3, because after all, what I did in that first row was I excluded numbers by multiplying them by 3. And so your space for how much you can kill in that first round is dictated by how far out you can go before multiplying by 3 takes you outside the numbers. All right, whew. I will stop there. That's it. Goodbye.